y'all doing today? As a reminder, we do have normal lab this week. It'll be about friction and work, so do make sure to report the lab as normal. Main thing for today is we're going to continue our rotation chapter by looking at centripetal force, continuing on where we left off last time. So before we get started, does anyone have any questions, needs, concerns, etc.? All right. In that case, let's pick up where we left off. We introduced the concept of centripetal force by examining these three scenarios, noticing that there is, in all these cases, a force causing an item to begin orbiting some point outside of itself. Here we have this tin can, here we have the moon, and here we have a bunch of cars. In all of these cases, these objects would normally want to move in a straight line, because Newton's first law tells us that's what all matter wants to do. Move in a straight line or don't move at all. So in each of these cases, some force has to play the role of keeping the items at a certain distance from the point that it is orbiting. Here it's tension in this string. Here it is the gravity from Earth acting on the moon. And here, in the case of all cars that are just turning, the force is when you turn the wheel, you change the direction of the force between your tires and the road, which causes some of the force to be directed inwards towards the center of this giant circle. The radius of that circle is what we call your turning radius. The smaller the circle, the smaller the turning radius. In all these cases, you need some amount of inward pointing force in order to make the turn happen. If that force was not there, these items would just all move in a straight line. The can would fly away in a straight line, the car would drive in a straight line, the moon would leave us and shoot into space in a straight line, which is bad because we need the moon. And the force responsible for this is called centripetal force. Now, lost my train of thought already. Happy Monday. The word centripetal, just to review, means center seeking. So when I say centripetal force, I'm referring to the fact that in all of those scenarios, there is a force pulling the item in question towards the center of this giant circle that it is now moving in. And even a car just briefly turning does still move like this. You just kind of enter the turn here and stop here, turn your wheel back and go back to normal. So a car turning is just part of the giant circle. But if you keep the wheel turned, you will eventually do a full circle. So we call it the center seeking, the centripetal force, because it is always pulling the item towards the center point of the giant circle that it is now moving in. And one of the quirks with centripetal force is that any force can play the role of centripetal force. Centripetal force is like a role in a play where any number of forces can play this part. To kind of go back to those pictures from a second ago, in each of these cases, a different force that we've discussed is currently acting in this part. Here, we have tension in this string pulling the can towards this person's hand, which I can replicate here with my little string of science. Got a cork on a rope here, and the string is what is pulling it constantly towards my hand in the middle. So in this case, tension is playing the role of centripetal force. But there's no rope between the moon and the earth. Here, gravity is playing the role of centripetal force. And again here, the force between your tires and the road is playing the role of centripetal force. So that is one of the weird things about this concept, is that any number of things can play the role of centripetal force. But what the formula is able to tell you is how much centripetal force is required to make a specific object turn at a specific turning radius while moving at a specific speed. A certain amount of force is required based on mass, speed, and turning radius. And in general, the more mass, the more centripetal force is required. The faster you're moving, the more centripetal force is required. And the smaller your turning radius, the more centripetal force is required. We're going to look at how all those numbers work together in a minute. Main points for right now. Objects want to move in straight lines. You have to force them to orbit like this. And whatever force is currently doing that, we call it a centripetal force, and it causes centripetal acceleration, center-seeking acceleration. Because turning in a circle like this is accelerating. Your linear velocity is constantly changing direction all the way around. You're accelerating towards the middle, but since you're also trying to move forward at the same time, you never really get any closer or any further away. The force is kind of acting like a leash to keep the item at a specific distance from the center. In the case of the string, it's a physical leash. The object can't get any further away. So the force is preventing the object from leaving, and its own velocity is compelling it to keep moving at that greatest distance. Still moving, it's just not escaping. As long as there is enough force to keep it at that distance. Questions so far? Okay. To briefly review these formulas before we start trying to apply them today. This statement is just a slight modification of Newton's second law. This just says that centripetal force is equal to mass times centripetal acceleration. If a force is acting as a centripetal force, the acceleration it causes will just be very specifically a centripetal acceleration. The center-seeking force causes center-seeking acceleration. And then, if you wanted to calculate centripetal acceleration, the needed amount of centripetal acceleration in order for something to make a certain turn is equal to its current linear velocity squared times the turning radius of the circle. And I do mean radius because the length of this string is the radius of the giant circle that the cork forms while it's moving in a circle. So in this particular case, string length becomes circle radius. And that's why we refer to turning radius, because you're turning in a giant circle. Now, centripetal acceleration is an acceleration. These things are accelerating when they're doing this. But you should think of the number for this less as a change in its speed and more a change in its direction constantly. The bigger the number you get for centripetal force, the more the item's direction changes every single second. So a very big centripetal acceleration indicates that the item is changing direction very rapidly, and that means it's probably doing a lot of laps very quickly. If something has a very low centripetal acceleration, it's not changing direction all that fast, and it's not making that many laps in a short amount of time. As an example, and we'll calculate this in a moment, this thing will have a pretty big centripetal acceleration because it's making laps quickly and it's constantly changing direction. The moon, despite being very big and having a very big linear speed, moon's actually moving several times the speed of sound, as it turns out. The moon's centripetal acceleration is actually very small because it takes it 24 hours to make one lap all the way around. It's not changing direction all that fast. If that makes sense. Now again, the main takeaways from today, the main things that I want to enforce in your brains before you leave the room today are that turning requires a centripetal force, and we're going to be exploring what factors affect that amount of force. Questions thus far? All right. Let's practice these formulas a little bit. Again, just to kind of show how the numbers play together, and then I'll switch this into talking about how those numbers affect your life on this planet. Let's put some numbers to the example of the cork on the end of the string, basically. Let's say that this mass is 1 kilogram. It's not, I'm just saying it is for simplicity's sake. And let's say that this string is 1 meter long. And I am now going to swing it above my head at 3 meters per second linear velocity. So a little something like this. And so this is a picture kind of the top down, seeing the circle from above. Mass of 1 kilogram, circular radius of 1 meter, because again, the length of the string is the radius of the giant circle, and a linear velocity of 3 meters per second. That's the speed the cork wants to fly away in a straight line at, but the string isn't letting it. I would like you guys to estimate for me, what is the required centripetal acceleration of this object? How much does it need to accelerate centripetally in order to constantly be making this turn? Very good. Show where that number comes from. Formula from the previous slide says centripetal acceleration equals velocity squared over turning radius. So that's going to be 3 squared over 1. Therefore, we require 9 meters per second squared of centripetal acceleration in order for this to work correctly. And again, this number describes how quickly it is changing direction. We'll have some comparison measurements in a moment. The unit for centripetal acceleration is the same as the unit for normal acceleration, meters per second squared. This is just a specific form of accelerating. So it just shares the same unit. It doesn't have its own unique one. But this is the required amount of centripetal acceleration for that cork to keep making this turn. And that centripetal acceleration comes from some amount of centripetal force. So how do we calculate that force requirement? Fc is equal to m times ac. Basically, a certain amount of force has to act on this mass to make it accelerate like this. Again, works the same as Newton's second law, F equals ma. So Fc, we have a mass of 1 kilogram, so it's centripetal acceleration of 9. Therefore, we require 9 newtons of centripetal force in order to physically make this happen. Just works out nice when you only got 1 kilogram. Water bottle out of the way of the board. This tells us that we need specifically 9 newtons of force to make this happen. If you cannot generate 9 newtons of force, the item's not going to orbit correctly. It would likely end up drifting away or taking off in a straight line if the string simply snaps. But in this specific case, before we start changing anything, that's kind of our baseline for right now. In order to be doing this repeatedly, I would need 9 newtons of force within this string. And in this case, it is again tension playing the part of the centripetal force. So when I ask here for tension, calculate here the required centripetal force to make this turn, tension is playing the role of centripetal force. So it is supplying this. So we have found the tension here. This is the needed tension in this string. And so to be doing this constantly, the string has to have within it and withstand 9 newtons of tension. That's our baseline before I start changing things. Sound all right? Okay, now, we're going to make some tweaks to this to try to show how all these various factors work together. What happens if you double the speed at which you are making this turn? What happens if we double the velocity of this object? So let's say we change nothing but the velocity. Velocity we're going to increase to 6, but the radius and mass will remain the same. What would change? All right. The centripetal acceleration, and also therefore the centripetal force, is going to end up quadrupling to 36. So instead of, you shouldn't erase anything in your notes, I'm just showing how it would transform. Instead of 3, we've got 6 squared over 1, 36. And in turn, if we plug 36 down into the force equation instead of 9, this would require 36 newtons of centripetal force. Doubling the velocity quadruples the required amount of force in order to make this turn. And so if I take this apparatus and physically swing it around more quickly, the string will have to have more tension in it. And I'm going to try to show that now, actually, because this string is tied to a force gauge. This gauge is designed to show you how much force is currently in the string. And so I'm going to now hold this correctly so you can see it. It's currently about zeroed out. So 12 o'clock is 0 newtons. I'm going to swing it at a pretty low speed. You see how much force the force gauge is reading? I can't actually see it. How many newtons does it say right now? Oh, about 2, about over here. All right. I'm going to make this thing spin faster now. I want you to see if the force changes.
Yeah.
Went up?
Yeah.
Scale max out? All right. To make a turn quickly, more force is required. And if you can't deliver that amount of force, you stop turning and you resume moving in a straight line. If this string couldn't withstand that much force, it's just going to snap, and the object will rocket away in a straight line. If you were driving in a car, notice, if you've driven, you've probably noticed and acted, When you were learning to drive, you were probably instructed and have been acting on the knowledge that you want to take sharp turns slowly, correct? If you're coming up at a light and you are just a 90-degree turn in general, you don't usually gun it and take the turn at speed, you usually slow down, right? Okay, you're allowed to make your life choices. I wouldn't encourage it though. The advice is to slow down before making the turn. If you do take the turn at speed though, like, again, I don't advise this, but if you're in a hurry and you don't feel like slowing down, when you do make the turn at speed, do you feel the increased amount of force involved? You kind of feel like your body's being pulled in a direction far more strongly than if you slowed down and made the turn at 10 instead of at 40. That's because at that higher speed, doubling the speed quadruples the force requirement. If you go 10 times as fast, that's 100 times the force requirement. And when you're driving, the centripetal force comes from the friction between your tires and the road. So if the tires in the road cannot generate that amount of force, you don't actually make the turn. You just try and then you keep sliding forwards and then bad things happen. Bless you. So, the faster you're going, the more force is required. This would end up becoming 36 newtons of force. Twice as fast, quadruple the required amount of force, and that's why you are advised to take turns slowly. The more force is needed, the more likely it is you're going to end up spinning or skidding out. It doesn't matter how good your engine is if you just cannot get the force and the friction into the road. So, taking the turn faster increases the force requirement rather dramatically, as it turns out. That concept good? All right. All right, I'm going to change the 6 back to 3, and then we're going to tweak something else instead. Now, last time we doubled the velocity. Instead, we're going to reset the velocity back to 3, and let's instead double the radius. What would end up happening then? Why did I pick up a second 3 marker? Now, instead of dividing by 1, we're dividing by 2. What would this do to our previous baseline of 9? Going to cut it in half, literally cutting it in half. Dividing by 1 does not change the 3 squared. Dividing by 2, though, is going to cut our acceleration and our force down to 4.5. Doubling your turning radius decreases the amount of required force. You may have noticed that the sharper the turn, the more you might want to slow down before making it, right? If you're on a town road turning at 90 degrees over a, like just a normal stop, like a city block, you usually slow down to like 10 before you make that. Well, you're advised to anyway. But the bigger the turning radius, the less that tends to matter. Freeways, over the course of several miles, highways rather, tend to turn a lot. But you don't really notice because the turning radii is huge. This radius would be like a mile or more sometimes if you're looking at the interstate from above. The bigger the turning radius, the less centripetal force is needed, and therefore the less you feel it and need to worry about it while you're driving. In turn, though, the smaller the turning radius, say we put 0.5 down here, we cut it in half instead of doubling it. Smaller the turning radius, the more force is required. So again, slow down going into sharp turns. I actually don't have this one on the board, but I've got one more slight wrinkle. Let's say that, let's reset everything. Any questions before I reset and change a different thing? All right, let's reset this back to 1 for the radius. So we're back to 9 for our centripetal acceleration. Instead of changing either of these two things, let's change the mass instead. We've been doubling things, we'll stick with that. Let's double the mass of the turning object. The centripetal acceleration didn't necessarily change. If you're taking the turn at the same radius and the same speed, you still need the same acceleration, but you're going to need more force to make a bigger object accelerate at that rate. So doubling the mass will also double the required amount of force. If you've ever driven a truck before and you noticed how awful the turns are, this is why. Trucks have more mass. Therefore, even if the centripetal acceleration requirement is the same, they need more force in order to make that turn. And again, there's only so much force you can actually manage between your tires and the road. So to compensate for the increased force requirement, Usually, if you're driving a truck, you tend to slow down when taking the turn, decreasing the AC to try to get the FC back down to something reasonable. So, does this paint a picture of how these factors at least affect cars? All right. Now, cars are not the only place where this sort of thing matters. So we've got one more number example before we try to wrap up our concepts for the day. These sorts of things play into the part of anything that is entering an orbit that is turning around some point. That again does include the moon, also includes the Earth around the sun, as it happens. Astronomers are constantly having to deal with this, tracking the orbit of things in space. But another slightly more terrestrial place where this sort of thing comes up is actually in fighter jets. If you watch Top Gun at all, I know that, how many years ago was Top Gun 2 at this point? I feel like that was last year, but was it 2 years ago? Point is, if you've absorbed any amount of fighter pilot media, be it documentaries or movies, you might be aware of the fact that pilots are only able to take turns in fighter jets only but so fast. And that's because the jet and the person in it can only handle so much acceleration before being rendered unconscious or dead. The human body can only accelerate so much before all your blood goes away from your vital organs and or you are rendered mush. Jets need centripetal force and centripetal acceleration to turn as well. So just as one more example, let's put some of those numbers to the test, see how absurd they get. We now have a 2,000 kilogram object. That's the mass of the jet. Flying at Mach 2, if you're unfamiliar with the Mach system, Mach 1 is the speed of sound, 343 meters per second. Mach 2 is twice the speed of sound, which would be 686 meters per second. So this jet's going Mach 2, generating sonic booms. Maybe it's just showing off. The jet is going to turn, and in order for a plane to do that, it needs to generate some centripetal force to cause the turn to happen. Now, up there's no road to turn the tires on in order to make that work. So where do you think the centripetal force on a jet comes from when it tries to turn?
Gravity.
It's not quite gravity. In fact, you still have to be fighting gravity in order to not fall out of the sky. Gravity is the centripetal force on the moon, though. Someone said something else.
Flaps on the wings.
Flaps on the wings, very good. This is true of commercial jets as well. If you've been on any sort of plane, have you noticed that when they turn, they have to physically bank their entire body? When they do that, they are changing the angle of their wings and therefore the flaps on their wings. And what that does is it takes some of their upward and forward thrust and changes its direction, like how changing the angle of your tires changes some of the force between you and the road as well. So it kind of works the same way as it does in a car, except instead of coming from the road, it's coming from the air. So the jet has to physically pivot its whole body to redirect some of its thrust inward to generate centripetal force. So again, in this case, the force playing the part of centripetal force is redirected thrust. And this plane is generating enough centripetal force such that the centripetal acceleration of both the jet and the person in it is 85 meters per second squared. That is one of the upper limit records that a pilot has done before being rendered unconscious. So this is, Maverick level stuff. And my question to you guys is, given these numbers, which these are fairly typical for fighter jets, and this is fairly typical if you're Tom Cruise. What is the turning radius of this jet? What is the radius of this giant circle that it is forming in the sky? What's the formula for centripetal acceleration?
$686.
Well, that's the velocity. What's the formula for centripetal acceleration?
Oh, velocity.
686 squared.
Squared divided by 100 squared.
Correct. So AC is V squared over R. Therefore, this formula would look like 85 equals 686 squared over R. And our goal is to solve for R. We want to know the turning radius. If you made the turn this fast and could withstand this much centripetal acceleration. So what kind of radius are we looking at?
$5,536 meters.
Yep. Which, if you're Canadian, is 5.5 kilometers. Which is a number of miles. A miles wide turning radius. And that number would get even more ridiculous if the jet was going even faster. Basically, jets don't tend to turn when they are going this fast, or they try not to, because there is an extreme amount of force required, and the turning radii just get absurd when you're moving this quickly. If you tried to decrease that turning radius, you drive up the centripetal acceleration, and then the pilot becomes unconscious and or jelly.
How many G's is that, you know?
Well, so this part here is the acceleration. So this would be about 8 to 9 G's, which again, ill-advised, but humans have withstood that while remaining awake. Infrequently, but they've done it. Yes? This? So this is the formula for centripetal acceleration. AC equals V squared over R. The maximum AC that this pilot can withstand is 85. The velocity they're currently moving at is 686. That gets squared, and we're looking for R. So to get R equals, the first thing we need to do is bring it over to the left so that it's not in the denominator. That would look like 85R equals 686 squared. Does that make sense? And then, since we still want R by itself, we have to get rid of this 85. And since it's on the top on the left side, we divide both sides by 85. And that gives us R equals 686 squared over 85. which if you put that in your calculator right, should give you 5,000, etc. This is not just true, this absurd turning radius is not only true of fighter jets though. If you've ever been on a commercial airline, you ever noticed how once you take off, the plane tends to bank slightly, and then it takes it feels like it takes absolutely ages as you are circling around the city before leveling out and heading in a straight line? Giant turning radius. So you don't even have to be breaking the speed of sound in order to need a turning radius that big. Planes have to move fast in order to stay in the air because they can't flap like a bird can. So at those big speeds, and considering that they can only have so many G's acting on them for the sake of the passengers and the plane not falling apart, you need a big turning radius to compensate. And I'll say again, if you are driving, smaller turning radius means more force. You are more likely to get thrown around in your car or skid out. As concepts, how does all this feel? All right. How do the numbers feel for right now? At the very least, the relationship between how going fast and small turning radius increase the needed amount of force. All right. Now, there's one more concept related to this principle that I'd like to address with you guys, namely to clear up any confusion about how it all works. I asked last Friday when I first said the word centripetal force if anyone had heard that term before. It's okay if you hadn't. What I'm curious right now is if that word sounds more familiar. Centrifugal force. I'm enunciating them weird to make the difference clear. What we've been talking about and calculating is centripetal force with a P. Centripetal, like a flower. And that is a real thing that you can actually calculate, and that's what we've been discussing all day. The word centrifugal force refers to something else, although it is a related phenomenon, and I want to address what each term means real quick. Centripetal, over there, means center seeking. Petal means seeking in some European root language. And that's why in every picture I've drawn here, I've mentioned that the force causing this to happen points to the center of the orbit. Centrifugal, the word fugal means fleeing. Fugal is the opposite of petal. It's the same century. The century means center for both words. But whereas petal means center seeking, centrifugal means center fleeing. The centrifugal force is referring to what it feels like when you feel like you're being pulled out of a circular orbit. Does that sound familiar? Or, no, let me ask one thing first. Have you ever noticed if you've been in a car, driving or passenger, and the car makes a turn way too fast? I kind of use this picture again over here. Say the car is going north and it starts turning left. If they take the turn way too quickly, you ever notice how as the car gets yanked to the left, you kind of feel like your body's getting thrown in the other direction? Does that sound familiar? Perhaps even more strongly if you frequent fairgrounds and go on tilt-a-whirls and things like that. The centrifugal force is referring to that thing that you're remembering, that sensation that happened. If I'm using this as a diagram again, and the car is turning to the left, there is a centripetal force pulling leftward on the vehicle, but the concept of centrifugal force is addressing that sensation you get that kind of feels like you are being pulled to the right because your upper body kind of yanks to the right as the car is moving to the left. Again, sound familiar? Might feel something similar again on any fair rides that involve spinning, or even just a normal merry-go-round analog metal one that you might have used at a playground, even a tire swing, really. As long as it spins, you might have noticed something like this. Like even possibly your arm getting thrown out and your blood kind of rushing to your fingertips. Any of that sounds familiar. That is what centrifugal force is referring to. This perception that you get when those sorts of things happen. And I want to address what this means and separate it from centripetal force, because centripetal force is a real thing that we measure and calculate, and centrifugal force isn't real. That's a hyperbolic statement, I'll admit. What I mean by that is, there isn't actually a force pulling you to the right when the car turns left. You do feel something, not arguing with that, but it's not a force that is literally pulling you to the right. I will elaborate. But when it says fictional here, it's referring to the fact that it's not really a force making this happen. You feel something, but it's not an outward force causing it. So when I say fictional, that's what I mean. There's a thing here, it's just not really a force. So, you are not a part of your car, correct statement? You are your own organism with your own body and your own mass. So when the car starts turning left, that does not necessarily mean that you immediately begin turning left as well. You are your own entity with your own mass, and that means you have your own inertia separate from the car. Kind of similar to that magician trick where you can pull the tablecloth out from under something. Just because the tablecloth starts moving does not mean the objects on top of it start moving. They have their own inertia that says stay still. So they're going to keep doing what they're doing until a great enough amount of force starts acting on it to make it change. So when you're in a car and the car starts turning left, your inertia doesn't know that immediately. Your inertia says keep moving this way. And that's what your body tries to do. Keep moving forward. And what happens is the seat beneath you and the seat belt yanks you to the left, and then the rest of your body is forced after it. There is a leftward force acting on you, but you still kind of feel like your body wants to go this way. This direction is technically forwards, north, but given that your entire perception is now being yanked this way, leftward, it kind of feels rightward. It's rightward given the fact that you are now moving left. It's rightward compared to what you were doing. But technically, your inertia is trying to take you forwards, the direction you were moving in. That's the direction your body wants to move in, and so that's the direction you start moving in until, again, the seat yanks this part of you leftward, and the rest of you gets dragged after it. So, the actual force acting on you points leftward, and it kind of feels like you get yanked to the right just because your sense of perception is now becoming more leftward. You're getting yanked to the left, therefore, your forward inertia kind of feels rightward. So the actual force here is, again, the leftward one. Your own inertia is just trying to carry you in a straight line, the same unchanging straight line. And it takes leftward force from the seat that you're in to make it change. You guys with me so far? All right. Now, that's all well and good, but that doesn't explain why you feel a rightward force, right? You still kind of feel a force. It feels like there's a force drawing you to the right, even though I keep saying the only actual force here is pulling you to the left. That rightward force stems from the fact that not only are you a separate item from your car, your body is not one solid item. You are also a bunch of separate items stuck together inside of your skin. Sorry for the image there. But you are, again, not one chunk of metal. You are bones and muscles and fluids all stuck inside of one bag. All of those separate parts of you have their own inertia telling them to keep moving in a straight line. So even if your lower body, seat belted into the car, starts getting pulled to the left, your upper body and all of the blood in it doesn't inherently know that until you get yanked to the left. Your blood wants to keep moving forwards, and it's going to go as far forwards as it can until it hits the walls of your veins and your skin. And so that rightward feeling force is actually just your blood pushing against the edge of your body as you're getting dragged this way. And again, from your new perspective, your blood feels like it's pushing to the right as it's trying to literally escape your body, but your skin doesn't let it. You can kind of mimic this if you just swing your own arm around and you feel your blood pooling up in your fingertips. You ever done that or noticed it happening? If you swing it around enough. It's the same thing. When you turn too hard like this, your blood, with its own inertia, tries to move forward, and therefore it's kind of pressing rightward against the edge of your body, but your body's getting dragged leftwards, and so your skin has to push leftwards on your blood to keep it inside of you. So all the exterior forces making you move do point to the left. The rightward sense is actually an interior force, which is incapable of making you move. Interior forces don't make you move. I can push on my own body all I want, but I don't go anywhere. So you feel something, you feel your blood pushing up against you, and you feel your arms trying to move in a straight line, but there's no exterior rightward force trying to pull you to the right. There's only the leftward force from your seat pulling you to the left. And this is why pilots get knocked out if they turn too fast. Because when you're doing all of this at Mach 2, all the forces are greater, and their blood tries even harder to escape their body, which tends to push all of their blood to one side of them, and very frequently that takes it out of their brain. And the human body does this weird thing where if your brain doesn't have enough blood in it, it knocks you out to try to get you level with the ground and get more blood to your brain. So that's why pilots, or really anyone turning any vehicle too quickly, rocket cars would do the same thing. If all your blood rushes not into your brain because of centrifugal force, you get knocked out. Normally it helps you fall over and get the blood back into your brain, but if you're stuck in a pilot seat, you can't really fall over to fix that problem. So anyway, I feel like I've been going all over the place today. The main point that I want you to actually take from today, the main points are centripetal force is real, and that's the force that does really pull you into a turn and keep you moving in a circle, causes real centripetal acceleration, and the numbers relate to each other as we've already mentioned. Increasing velocity increases the force, increasing turning radius decreases the force. Centrifugal force is not what we talk about in here because it's simply a perception based in a glitch of human body design. You only feel centripetal force because you are a being with blood in you. And as it turns out, the only ways that human can perceive force is pressure on your skin, because all of your nerve endings for force are in your skin. So you only feel force when it's acting as a pressure upon your skin. And that's why you feel internally your blood pressing against you. And that's where the perception of centrifugal force comes from. But it's not a real force, it's not an external force. It's a sensory phenomenon based on a glitch of human body design. This is the real thing. This is what we actually deal with in here. I wanted to make that clear. Sound good? All right. I will say though, this word is the root word for centrifuge, which is the machine they use to separate your blood into its component parts. Because, yeah, it's the spinny thing you put the test tube in. Literally, all the particulates get rushed to the bottom end of the tube, like how your blood rushes to the end of you when you're turning. So, useful to understand the difference. On Wednesday, we will talk about torque, which is a different way that force can make things spin. And that's going to be it for today. Report to lab as normal. Let me know if you need anything. Have a wonderful day.